So today I'll talk about learning linear dynamical systems with Hankel nuclear norm regularization. So you will see that it's actually a use of low rank matrices, but in particular low rank Hankel matrices. This is a joint work with my graduate student, Yue Sun from University of Washington. And we collaborated with Samit Oymak, who's a professor at UC Riverside. All right, hopefully I can now advance the slides. Okay. Yeah, so let me motivate the question that we will be looking at, which is the system identification or learning a dynamical system using low-rank Hankel matrices. Let's motivate that by looking at several different application areas where such a problem comes up. So in the first top corner, you'll see that the main problem we will talk about today, which is linear time invariant system identification, which basically means when you are able to apply a time signal as input, some adjacent areas to system identification, such as the second example on the top right corner is about shape from moment estimation problem, which is a problem in signal processing. In particular, comes up in tomography and geophysical inversion problems, where a low-rank Hankel matrix comes up. And interestingly, there is some interpretation to the rank of the Hankel matrix in this area. For instance, for geophysical inversion, the rank of the Hankel matrix is the number of corners of a polytope-shaped region underground that you're trying to infer from geological measurements. So number of vertices corresponds to the rank of the Hankel matrix. There are other applications as well. The in-video in-painting application is really similar to low-rank Hankel, low-rank or low-order dynamical system identification, but it uses a low-rank dynamics fit in order to fill in missing videos, missing frames in a video. And furthermore, also in super resolution, also a signal processing problem, where you are trying to find or decompose a signal or recover a signal that has only a few complex exponential terms. So it has a sparsity in the frequency domain and continuous frequency domain, and therefore super resolution problem. One of the approaches to super resolution by Chen and Chi has used low-rank Hankel matrices. So with that, let us focus on the input-output system identification as our main application. So this is a classical problem. It goes back to the 60s. And in classical method, generally, the approaches are based on solving a very largely squares problem, essentially, basically stacking your input and output together and solving a least squares problem that tries to identify the linear mapping between the input and output. And typically, if you want the system to be low order, you would then do something like SVD plus truncation of singular values or a projection. And this is the basic idea of matrix pencil methods and subspace system ID methods. Subspace system ID follows this approach by a way of finding the ABCD matrices, which we will show later. And this goes back to basically Kalman and Ho in 1966, so classical method. And there has been a lot of variations and improvements on this, but essentially it shows that this problem is important, and the dimension of the system and its choice and the fact that many real systems are low dimensional are also very important, and already present in these methods by an SVD truncation. But more recently, an approach became popular where you try to incorporate the fact that you want the system to be low order, the dynamics to be low order, by penalizing the nuclear norm of a Hankel matrix and adding it to the least squares optimization. And this approach was used by several recent papers. A paper that Tin-Kei Pong and I have in 2013 looks at this problem and a variety of different applications that can be modeled as this, and talks about algorithms to solve the regularized problem, but does not focus on statistical and sample complexity guarantees. There are also other papers by Lieven Vandenberg's group, as well as other groups, Anders Hansen, and others, where they empirically used nuclear norm regularization and observed good behavior, but none of them had theoretical guarantees about the approach. So our goal here today is to try and explore some statistical bounds concretely meaning sample complexity. How many samples do you need to guarantee a certain error rate in the recovery of the system? And we'll talk about what metrics we will use. So that's our goal. One reason to revisit this problem from a statistical point of view is that there has been a recent flurry of activity in this area of learning dynamical systems. And all the existing work, this is a kind of a long list of them, are focused on just least squares, unregularized least squares. And even the unregularized least squares has been explored only recently in terms of sample complexity. And so it's not very, so yeah, as you can see, all the papers that are giving results for even least squares are pretty recent. And there are different categories of these papers. So the first batch of papers here are assuming that you can observe the state of the system. So it's not only input output. And that's a slightly different problem. It doesn't involve Hankel matrices, and guarantees are given for least squares fits. And there are the different papers focused, for example, on stable versus unstable systems, on the input being random or input being a designed signal, on whether we want to identify, whether our end goal is to identify the dynamics, or it is to actually control the system, or it is, for example, to predict the output. And there are some extensions to nonlinear dynamics as well. The second batch of works cited here are working with input-output data. That is the setting that we will also consider. And here also the various papers are all about least squares only, no regularization. And they look at different setups where you have strictly or marginally stable system, no results for unstable as far as I know. Also random versus designed input, and also what the end goal is, control or identification or prediction of output signal. And there is another paper, interestingly, from a signal processing literature on super resolution that is by Kai and Xu and co-authors, so Wei Yu Xu and Jiafeng Kai and co-authors, in which they actually look at Hankel regularity similar to the 2016 paper, but for a setup of system identification that these prior papers looked at from a least squares perspective. So what's the problem? Here's a system identification problem in its simplest form. So here we are assuming a single input, single output system. So the input UT and output YT are scalar vectors or scalar systems, and X can be a vector of dimension R. Yeah, so this is the dynamical system where UT is the input signal, YT is the output, and the A, B, and C denote the dynamics of the system, and CT is an output measurement noise. In this model, we say so for such a system, we say the state space model is of order R when there exist A and B and C of sizes given by R. So A matrix is R by R, meaning that the X vector or the number of states is also R. This is the minimal number of states corresponding to this input output signal will be R. So when that's the case, we can also characterize this linear system fully with its impulse response and a to the power I minus 1 times B. And these are also known as Markov parameters. And the order of the system, this capital R, corresponds to the rank of, oh, there's a typo here. It's the rank of the Hankel. Oh, no, actually, it's right. Hankel matrix of consisting of the elements of the impulse response. So arrange the impulse response in a Hankel matrix, meaning a matrix that is fixed across the anti-diagonals like this. And its rank will be the minimal order of the system. So meaning that as you increase n, the rank of this Hankel matrix will not increase. The size can increase, but rank will be R. That's the order of the system. And this notion is not just for size, so it extends to MIMO systems, and it also extends to MIMO systems via block Hankel formulation. Okay, so this is the basic problem we are interested in. Now, the input-output mapping can also be represented by a convolution. So output signal Y is a convolution of input U with the impulse response H plus noise. We define the SNR to be the average power of the input divided by average power of noise. And because the length of input is 2n minus 1, there is this scaling. Now, the question is, how are we sampling our system? There are two different data acquisition models that we will talk about and are used in literature. So one shown on the left side is a multi-rollout setup, which means we can apply different input signals U to the system and let the system run, but at a fixed time step, like 2n equals 2n minus 1 mentioned here, we get to observe the output. So you get a single observation of the output for each of these signals. This, for example, corresponds to, suppose you have a chemical system, a chemical reaction, and you throw in a new nutrient and you sit for a while, then make one measurement of your system. So this is one model. Each of these inputs is called a rollout. Another model, maybe more typical one, is on the right, which is a single trajectory measurement. So the input signal is applied continuously and the points on the output are measured also all across the trajectory at certain sampling time. So in either of these models, basically when we talk about sample complexity, we mean the number of red dots, the number of times we had to measure the output. So that makes the notion of sample complexity sort of consistent between these different setups. So, and yeah, so a lot of times actually the cost of measurement is also each time that you read off the Y, so physically also makes sense. So we can rewrite this problem in a little more convenient way by replacing the convolution with a matrix form. Here for the multi-rollout setup, the matrix U that appears here is of this form where each signal appears as a row of the matrix. Each of the inputs that we applied is a row. For the single rollout case, our U is also a Hankel matrix where we have put the entries of the one single U signal that we have from U1 to U capital T arranged in a Hankel matrix. So this is of size 2n minus 1 by T. But in either case, we have basically a linear set of equations, what the classical methods do. Loss, we take the squared loss, but we add to it a regularization term, which is the nuclear norm of the Hankel map corresponding to this impulse response. And we look for the solution to this optimization problem. So remember that H of A like this, and it uses impulse responses up to 2n minus. And known low rank recovery, matrix recovery results are, for example, order of n times R if you have random Gaussian measurements of a general rank R matrix for unstructured matrix. But if we have a Hankel matrix, the Hankel structure allows us to use a lot less samples to recover a Hankel matrix, and this would be order R squared. This by itself can be shown by adapting a result from the Kai paper that I cited earlier. So we will use this in the result that we will obtain. But it's important to point out that it's a low rank matrix recovery problem, but because of the Hankel structure, we have a lot less sample complexity. Let's also determine what metric do we want to use for judging how good the system recovery is.
Maryam, sorry, just a quick question. So the results that you said were for the single trajectory case or the multiple rollout?
A multiple rollout, actually. Okay. The one I quoted, we will get to it later. But in general, how do we judge how good the recovered impulse response is? We can ask for L2 error between the impulse response recovered and the true impulse response. Or we can also look at the spectral error in the Hankel map. So if you're recovering H hat, you can look at the spectral norm error in the Hankel maps corresponding to that. And these two error measures are a bit different. The second one has been studied a bit less, but it's actually quite useful, particularly for model selection and for finding a realization, because the singular values of the Hankel matrix and truncating them is a typical way to select model orders. So essentially, a singular value gap in the Hankel matrix is critical. So this measure is actually pretty helpful, more helpful than the L2 recovery error. Essentially, Hankel spectral error is always an upper bound on the L2 error, but we show that they're actually close to each other order-wise. So here's the result about the Hankel spectral recovery error. Suppose the Hankel matrix is n by n, and R denotes the system order, T denotes the total number of samples, meaning the number of output measurements. Then we have the following bound on the spectral error of the recovered Hankel matrix. So there are two regimes. The top regime is when the number of samples is bigger than order of R squared. And we are hiding log factors by these tilde inequalities, by the way. So when T is larger than order of R squared, the error will be scaling as n over the SNR times T square root, which is the right order to have. It's actually optimal, so, as in, for example, studied in the paper by Oymak and Oze. And in the regime where T is between R and R squared, so a little bit lower sample regime, we get a bound that is a little bit suboptimal. And we don't actually know whether we can fully drop to a bound that also scales with just without the R or not. But it's plausible that this can be sharpened. So the second line here is an extension from the paper, uses basically a result and extends it from the paper by Kai et al. So this means that the minimum sample complexity is R and not N. It could be much, much less than N, meaning we have this second line error guarantee if we have only order R samples. So that is good news. It basically is saying that sample complexity can be as low as possible. And yeah, let me again, since Pablo also asked earlier, remind you and maybe be very clear that we are talking about this multi-rollout setup here in the theorem I just mentioned, which is you apply different signals and you take one output measurements per signal. More generally, one may be interested to take multiple points of measurements in these multiple signals, but for simplicity, the first case is the one that we take one output measurement per signal. So this result, yeah, is for that.
I'm sorry, a quick question about this. Do we expect this dependence on N? Because somehow the more samples that I have, the error gets bigger. So shouldn't I want, I mean, does this Hankel norm actually?
Right, because N is the size of the Hankel matrix, and it does show up in the error bound itself. But what's important is that T doesn't depend on N. T depends on N very little. See, so the number of samples is R in the lower regime and is R squared in the upper regime. So number of samples scales as we want, but the error bound itself does have N.
I see. Okay, thank you.
Yeah, thanks for the question. Yeah, feel free to interrupt if there are any questions. And the Oymak paper by Oymak and Oze also gives an L2 error bound of the same order for the unregularized least squares. And what we are showing is that with enough samples, meaning R squared order of samples, which could potentially be dropped to R, what our current result is as is, we get the same spectral norm error that scales similarly. Well, actually, let me skip this one since I'm running a little bit short in time. We also have a result for a regularized least squares problem. So regularize these squares using only one trajectory, so single trajectory sample. So this is a bit different from the previous setup. Here, for this result, we ask that there are two recent papers, one that provides a naive spectral error estimate, so their spectral error bound wasn't optimal, and for least squares. for the spectral error. So a spectral error scales correctly, but not the sample size. And we ask whether we can get both. And here's a result we have for this. So again, the size of the Hankel matrix is n by n. Total number of output observed points are t. H hat of LS is the least squares estimate. So this is not with regularizer. This is just the least squares. And here we need to assume without regularizer that t is on the order n. Then the spectral norm error actually obeys this scaling, which the takeaway from this one is the spectral error is as good as the impulse error, impulse response L2 norm error, even for just these squares. So this is a side point about improving the least squares result. Let's put together all our results in a table to kind of contrast things. So again, the setup is the Hankel matrix is n by n. System order is R. Number of samples is T. And the noise level sigma, which we've used in this table, is 1 over square root of SNR. The LSIR stands for using least squares to find the impulse response directly. And the LS Hankel is the regression problem that solves for the Hankel matrix. So there are two different least squares setup that these two papers that we are citing are using. They're actually both least squares, but different least squares problems. And we contrast this. So these two columns at the end are existing work, Oymak and Ozay paper that has sample complexity n. It uses a least squares that regresses for the impulse response. The L2 error is scaling as sigma square root of n over t. And the Hankel spectral error, though, was scaling not optimally. It was proportional to n. So in terms of Hankel size, it was not optimal. So if you look at the second column here, that is in contrast our result for least squares, which improves this part of the bound to be optimal. The dependence on n is square root of n. N is the Hankel size. Now, the other paper, the last column, Sarkar, Raklin, and Dahle, does have a result for Hankel spectral error. But the only thing that they miss is that they have a 1 plus sigma factor in front. So even if error goes to 0 or noise is 0, you still have a spectral error. The spectral error does not go to 0, whereas in our result, it does. But maybe more importantly, more contribution here is the first column. So here, this is for regularized optimization. We are regularizing with nuclear norm. We proved that the sample complexity is R squared, and this is in contrast to all of the least squares problem, where you have to push up T to be of equal size to the Hankel matrix, so n or even n squared. The nuclear norm regularized will have R squared. It will have the impulse response error that. So optimal guarantee is obtained for the least squares for impulse response, and good guarantees for the T in the R squared regime. It's still open whether this can be done with T less than R. The regime between R and R squared has a good bound, but it's not optimal yet. So that is still open. Can the dependence be improved? For nuclear norm error can be improved. And also whether the dependence of the bound itself on n can be improved. There's actually a good question that in these squares, you're stuck with the n, but with nuclear norm regularization, can you totally remove the n? We have not. We are still stuck with the n, but that's a good question. Actually, that's what Pablo also asked earlier. Now, to actually see the complete picture about system ID, we need to mention how this optimization problem is used. And this is in the context of model selection. So when you use the regularization method, which is the optimization problem on top, you do need to tune the lambda, meaning you have to try different lambdas and find the optimal one. And then for the optimal lambda, you get the optimal error bounds. Similarly, in the least squares approach, if you do not regularize, you will be tuning the n. You try many different sizes for your Hankel matrix to try to determine which one gives you the lowest error. And essentially, you will be solving a training validation algorithm, sort of as the following algorithm. take the training data, which will be the U and the Y. Y has T measurements, and then take validation data that has T val measurements, and the hyperparameters, which are the dimension of the Hankel or the regularization weights. So we assume that for dimension of Hankel, you can go from 1 to R or a multiple of R. And for regularization weights, you have a set of numbers that you can try. For example, it's a one-dimensional interval divided into, for example, different values. So then one solves the training problem, which is solve the regularized least squares problem over here and find the H hat corresponding to that lambda I. And in the end, after you have them, you will pick the best lambda I. This is actually an offline validation algorithm. There is actually an interesting observation about an online version of this, which shows the role of regularization, which I didn't include on this slide, but it says that when you're regularizing, tuning lambda results in lower overall number of samples compared to tuning n. So while it's possible to not use a regularizer and try to tune the n, in the end you pay with higher samples. So I have some backup slides on that if you wanted to discuss, but since I'm kind of short on time, let me show you some experiments. So this is an experiment showing the regularization and the least squares compared with each other versus 1 over lambda. So this is for the regularized problem. We are tuning the lambda. The training error always goes down as the lambda decreases, but the validation error, which is the orange curve, as expected, will go down and then start to go up. And typically in engineers in practice will plot this curve and then look for this corner point and pick that as the tuned value for lambda. We see that this curve, by the way, the validation curve does not have any sudden jumps, and it's fairly smooth and slowly varying, which kind of also results in empirically tuning lambda is easier because you don't have to zoom in a very narrow region. The plot on the right shows the same when you're tuning the Hankel size, the Hankel matrix size. And the bottom curve again is the training error and the top is the validation. So this is these squares only without regularization. And the validation curve is a little less nice. And this is a very small problem, but we can see that it's pretty sensitive to picking the right order. So that's empirically one reason people have preferred to tune the lambda in the regularized formulation compared to n in the squares. So, okay, so this is, by the way, this is actually a single trajectory data from DAISY dataset. That is a data set of various dynamical systems input-output data. And it's pretty small, but it's for illustrative purposes. And we can also show what happens in the time with the time signal. So if you want to predict output trajectory with regularization and without regularization, when you have a lot of training data, both of them work well. You don't really see a difference. So here, the training size is 200, test size is 600. Because this system was very low order, we can get away with this very small training set size. But still, this is not close to the minimum required. I believe this system was order 3. Yeah, order 4, actually. Yeah, you can see it here. This is the same system. And this plot actually shows the difference between regularization and no regularization much more clearly. So this is the spectrum of the Hankel matrix recovered with regularization on the left side. And the n chosen, the Hankel size, is 10. The order of the system is 4, and that's actually coincides with the true system order for this particular example. And we see that the Hankel matrix has a very clear gap in its spectrum. So there will be no confusion about the system order being 4 when you use a regularizer, because it tries to push towards a low rank Hankel matrix with the regularizer term. If there is no regularization, the system is kind of close to 4, but it's much less clear, because the singular values do not display a big gap, at least when we are fixing the size to be n equals 10. And if we go with that recovered solution with the two Hankel matrices I just showed the spectrum of, our predictions will also be off with without regularizer. So with regularizer, the time series prediction is kind of becomes arbitrary in this setting. Where do you want to cut off your, where do you truncate the SVD of the Hankel matrix? So this is just for a fixed Hankel matrix size. But again, there can be discussion about the full loop of training and validation, as I was just saying. This is just one snapshot for fixed size. And this is an example which we tried a nonlinear system. So this whole theory is just for linear dynamics, but just for fun, we tried it empirically for a nonlinear system that was linearized. This is the inverted pendulum. And the linearized model can be identified with similar approaches. And the regularized one is better predictor, again, with a fixed Hankel matrix size. That's the spectrum for that one, the Hankel spectrum for the nonlinear system. Again, a clear gap whenever we use the regularizer. And I'm kind of running out of time. Let me just conclude by summarizing. So nuclear norm regularization is used in practice, at least in subsets of control theory community. But it's poorly understood in the sense that statistical guarantees weren't available for it. And in terms of, for example, error rates and sample size. One of the empirical benefits of it is that it simplifies model selection by having to just tune the lambda and not change the size of Hankel matrix. And that because there's the typical validation curve plotted versus lambda is less sensitive, it's flatter, it's less, the training or the tuning is less sensitive. So these are some empirical benefits that encourage people to use nuclear norm regularization. But what was new in our work is that we were able to prove new estimation error guarantees. We gave improved guarantees for nuclear norm recovery, improved compared to the signal processing result I pointed out in the beginning for recovery of sum of exponentials. And that we also gave optimal Hankel spectral error bound for the least squares. So we made an improvement on just least squares approach as well. There's still a lot of questions open that we would like to look at in the future. For example, better understanding of this empirical behavior, of the spectral gap and sensitivity and so on. How can we formalize that and prove a theorem that says something specifically about the bigger spectral gap gives you this benefit? And can errors in the statistical error I showed you in the low sample regime be improved? There is some room for improvement there. And finally, end-to-end sample complexity. So we have some preliminary result for this. This means that if I actually don't know the system order and I'm fully running the loop of model selection and so basically training and validation with tuning the hyperparameter. And while tuning the hyperparameter, your algorithm can request new samples. In this setup, regularization helps reduce overall samples, but this is actually just a preliminary result. So hopefully our next version of the result will actually show how regularization helps with the overall sample complexity. So with that, I'll stop here and I'm happy to answer any questions.
Great, Maryam. Thank you so much for a very nice talk. We have one question in the chat. I'm not sure, Ivan, Ivan, if you want to ask this directly or
yes, I think it's related to your question, Pablo. So what is the role of N in this method? I think it has to do with the truncation of the infinite impulse response. Is it correct?
Yeah, that also plays a role. That's right. Yeah, exactly. So when you pick the size of the Hankel matrix B n by n, it means that you observe the impulse response up to 2n-1 only. Essentially, you're truncating at 2n-1. Yes.
So this means that there is bias involved in the method because there is truncation error.
Yeah, so both the least squares method and the regularized method will have that, but the regularized method is basically not suffering much from it because you can fix the n and the number of samples you need will be only related to the rank, which is R, which can be much smaller than n. So fix the n in your optimization problem to some large number and not worry about it. Whereas the least squares method will have to carefully choose the n.